Introduction to Inverse Trigonometric Functions. Hello everyone. Let us begin our session on inverse trigonometric functions. To start, let's look back at our previous study of trigonometric functions. We observed that functions such as sine of x, cosine of x, and tangent of x are periodic. In simple terms, being periodic means that these functions repeat their output values at regular, fixed intervals. Now, this creates a challenge when we want to find an inverse. For any function to have an inverse, it must be a bijective function. This means it must satisfy two conditions. It must be one-to-one, where every unique input produces a unique output, and it must be onto, meaning every possible output in the range is covered. However, as we have seen, trigonometric functions are many-to-one. For example, the sine of 0 is 0, and the sine of pi is also 0. Since different inputs can produce the same output, these functions do not naturally have inverses over their entire domain. To solve this problem, we use a technique called domain restriction. We limit the domain of the trigonometric functions to a specific, narrow interval where the function behaves as a one-to-one function. This specific restricted range of the inverse function is what we call the principal value branch. Understanding this concept is vital, as we will see in the next few slides, because it ensures that for every input, we get one unique and consistent output. Understanding constraints in inverse trigonometry. Now that we have established why we need to restrict the domains of trigonometric functions to make them bijective, let's look at what this means when we actually solve problems. First, it is important to understand that when we work with inverse trigonometric functions, we are not searching for every possible angle that could satisfy a given ratio. Because trigonometric functions are periodic, there are infinitely many angles that could give the same value. But for the inverse to be a true function, it must provide only one unique output. This unique output is what we call the principal value. Furthermore, you must keep in mind that the various properties and identities we will use with inverse trigonometric functions are not universally applicable. They are only valid if the input value, x, and the resulting angles fall strictly within these predefined boundaries. If we ignore these constraints, our calculations will be mathematically incorrect. In the upcoming slides, we will define exactly what these boundaries are for each function and see how to apply them in practice. Concept of domain and range. Looking at the slide, for any inverse function, which we denote as f inverse of x, there is a fundamental swap that occurs between the original function and its inverse. First, the domain of the inverse function, f inverse, is exactly the same as the range of the original function. F, in simpler terms, the set of possible outputs from our original function, becomes the set of allowed inputs for the inverse. Secondly, the range of the inverse function, f inverse, is the restricted domain of the original function. F this is where the concept of the principal value branch comes into play. The specific interval we chose to make the function one-to-one now becomes the only possible set of outputs for our inverse function. Now that we understand why we must restrict the domains of trigonometric functions to make them bijective, let's look at the general mathematical rule that governs all inverse functions. Understanding this relationship is crucial because it provides the theoretical foundation for the specific values we are about to examine. In the next slide, we will apply this general rule to the specific trigonometric functions to see their actual domains and principal value branches. Table of principal value branches. Now that we understand why we must restrict the domains of trigonometric functions to make them bijective, let us look at the actual standards used in mathematics. To ensure that every mathematician and student arrives at the same unique answer, specific intervals have been standardized as the principal value branches. Please refer to the table on your screen. First, let's look at the inverse sine of x. Its domain is the closed interval from -1 to 1, and its principal value branch, or range, is from -pi/2 to pi/2. Next, for the inverse cosine of x, the domain is the same, -1 to 1, but the range is different. It spans from 0 to pi. Moving to the inverse tangent of x, you will notice the domain is all real numbers. However, pay close attention to the range. It is the open interval from -π/2 to π/2. The open brackets here mean that the endpoints are not included. Similarly, for the inverse cotangent of x, the domain is all real numbers, and the range is the open interval from 0 to pi. Now, let's examine the reciprocal functions. For the inverse secant of x, the domain consists of all real numbers except for the open interval between -1 and 1. Its range is from 0 to pi, excluding the value of π/2. Finally, for the inverse cosecant of x, the domain is also all real numbers excluding the interval between -1 and 1. Its range is from -π/2 to π/2, but we must exclude 0 from this set. It is crucial to memorize these boundaries because, as we will see in the next few slides, using an angle outside these specific ranges would mean you are not finding the principal value. To help you visualize why this uniqueness is so important, let's move to a real-world analogy involving GPS coordinates. Real-world analogy, the GPS coordinate. Now, to help you visualize why we need the restrictions we just discussed in the previous slides, let's look at a real-world analogy. Imagine you are using a GPS system. When you enter a specific set of coordinates, you expect the GPS to lead you to one single, unique location on Earth. Think about how confusing it would be if those coordinates were periodic, meaning if the same set of numbers pointed to 5 different cities across the globe. In such a case, the system would be completely useless because it wouldn't provide a definitive, single destination. Similarly, the principal value branch acts as a unique coordinate for inverse trigonometry. By restricting the range, we ensure that for every input value x, there is exactly one unique output angle theta. This eliminates the ambiguity of the periodic nature of trigonometric functions, which we will see in action in the next slide when we evaluate a specific example. Step-by-step example, evaluating a principal value. Now that we have understood the theory and the standardized table of branches, let's put everything into practice with a concrete example. We are going to find the principal value of the inverse sine of 1/2. First, we must check the domain. As we saw in our table on the previous slide, the domain for the inverse sine function is the closed interval from -1 to 1. Since 1/2 falls within this range, the expression is mathematically valid. If the value were outside this range, the expression would be undefined, which is a common mistake we will discuss in the next slide. Next, let's set up the equation. We can let the inverse sine of 1/2 equal theta. This is equivalent to saying that the sine of theta equals 1/2. Now, this is the most critical part, identifying the principal value branch. Remember our GPS analogy? We need a unique coordinate to avoid confusion. For the inverse sine function, the range is restricted to the closed interval from -π/2 to π/2. Therefore, we must find a value for theta that lies specifically within these boundaries. Finally, we determine the angle. Referring to our standard trigonometric table, we know that the sine of π/6 equals 1/2. Since π/6 falls comfortably within our required interval of -π/2 to π/2, it is indeed our principal value. Thus, our final answer is that the inverse sine of 1/2 equals π/6. Common mistakes to avoid. Now that we have walked through a practical example, let us discuss some common pitfalls to ensure you don't make these mistakes in your exams. First, let's talk about ignoring the range. A very common error is providing any angle that satisfies the trigonometric ratio. For instance, if you recall your trigonometric table, you know that the sine of 5π/6 equals 1/2. However, the inverse sine of 1/2 is not 5π/6. This is because 5π/6 falls outside the principal value branch, which we defined as the interval from -π/2 to π/2. Always remember to check if your answer sits within the restricted range. Next, be mindful of domain violations. You might encounter a problem asking you to calculate the inverse sine of 2 or the inverse cosine of negative 1.5. You should immediately identify these as undefined. As we saw in our summary table, the domain for both these functions is strictly between negative 1 and 1. Since 2 and negative 1.5 fall outside this interval, these expressions are mathematically invalid. Finally, pay close attention to the notation of the brackets. It is easy to overlook, but it is crucial. Note that the inverse tangent and inverse cotangent functions use open intervals, indicated by parentheses. This means the boundary values, such as pi over 2, are not included in the range. On the other hand, the inverse sine function uses closed brackets, meaning the endpoints are included. Keeping these 3 points in mind will help you avoid the most frequent errors. Now, let's move on to the final summary of the chapter. Key takeaways. Now that we have covered the theory, the examples, and the common pitfalls, let's wrap up this session with the key takeaways from this lesson. First, let's revisit the concept of bijectivity. As we discussed at the very beginning, a function can only have an inverse if it is bijective, which means it must be both one-to-one and onto. Since trigonometric functions are naturally periodic and repeat their values, we must restrict their domains to a specific interval to satisfy this condition. Secondly, remember the principal value branch. Just like the GPS analogy we used earlier, this is the specific, standardized range of the inverse trigonometric function. It is what ensures that for every input you provide, you receive one unique and consistent output angle. Third, let's talk about validity. This is a critical point to remember when solving problems. Any property, identity, or simplification you apply to inverse trigonometric functions is only valid if the input value, x, is within the defined domain and the resulting angle falls strictly within the principal value branch. If these conditions aren't met, the result will be mathematically incorrect. Finally, regarding standardization. To avoid the errors we discussed in the previous slide, always refer back to the standard table, such as the one provided in your NCERT textbook, to confirm the exact domains and ranges before finalizing your answer. Keep these 4 points in mind, and you will be able to handle inverse trigonometric functions with precision.